Hello, Chem 2. Welcome to another edition of Gas Laws. Hopefully everyone is safe and taking care of themselves with Governor Hogan's recent stay at home. You have more opportunities to watch some fun-filled chemistry videos, listening to my voice, and trying some owl problems, or not. Anyway, today what we're going to do is connect stoichiometry with gas laws. So this is the part where it relates amounts of volumes of gases in reactions. That's what we're going to do today. So administrative pieces, just as an aside, a little sadness, we are missing another lab at this point called the butane lab. But what I've done on OneNote is I've made links to both the molar volume lab and the butane lab that was done online by people to show you what we would have done in case you wanted to take a look at that and see what the process was. Both are former AP labs. The AP has changed their format of what lab requirements are, but they're both former AP labs. They're really, really good. They work really well, and I'm very disappointed that we weren't able to do them. There's the OWL homework and the like, and then announcement starting tomorrow. And we're going to try this week under this format and see how it works. I'm going to have flex hours. I'm going to initiate a team chat meeting starting at 2 o'clock and scheduled to go till 2:45, maybe 3 o'clock. That's the office hours are 1 to 3. And splitting the two classes. Chem 1 is from 1 to 1:45, and then Chem 2 is from 2 to 2:45. Now, if the classroom, since we have 50 total kids, gets a little too crowded, I may have to split and have a 30-minute Chem 2 Mod 3 and a 30-minute Chem 2 Mod 4. We're going to treat it like a flex mod. Come with questions. If I have anything I want to mention about what's going on in the time being, have a little bit of an announcements, but for the most part, it's for you guys to ask questions about the OWL problems and the like. It'll be a little disjointed because I'll need to go back and forth between looking at what OWL problems you have. My suggestion is bring a piece of paper, bring something to write on so you can share what you've done. So we can take a look at it and get the most out of this time. It's going to be a learning curve, a learning process. So be patient, but I'm going to try to establish some way for us to get a little bit of quote unquote face-to-face time. So starting tomorrow, 2 o'clock to 2:45, we're going to do our flex hours for Chem 2. Looking forward to it. A little anxious, but we're gonna make this work. Okay, let's see what we're doing today. This chapter is chapter 5, which is the gases, and we're going to be doing this section 5.4 today, stoichiometry of gaseous reactions. As an aside, we've already done gas mixtures. That's a Dalton's law, so we're going to kind of skip over that before tomorrow's lesson. But today is all about stoichiometry. So ideal gas law, we mentioned, was the PV equals nRT. And it has the opportunity to have the pressure, the volume, and the temperature and connect it back to moles. That was what we started when we did stoichiometry. It was always how do we go from grams to moles, particles to moles, volume to moles. This time for any gas, we're going to go from pressure, volume, and temperature to moles. Or if you have moles, be able to get either one of the other three. And mentioned in the last video about the different gas law constants. I'm going to use 8.314 and 0.0821 a lot. Those are the ones I find most convenient. If you want to memorize the other ones, you can. So I affectionately refer to this as Godzilla meets Mothra, two beasts of the chemistry world. Stoichiometry and all that was, meeting gas laws and all that has been for this time frame that we've been off, and bringing the two together. So stoichiometry with gaseous reactions, we're going to need a balanced equation just like before. We're going to relate moles of two different components. It's just how do we get those moles and what do we do with those moles is going to be the crux. A way that I look at it is this is what we had. Had is the operative term. This is what we had. We had the ability to go from mass to mole to mole to mass, or volume to mole to mole to mass, or volume to mole to particles. We have all this options of where to go within our measured quantities of a given proportion versus a asked for value measurement. But This number, 22.4, we remember that was very specific to two conditions. Condition number one had to be gases. That's still going to hold true. These two are going to be volumes of gases. But the other condition was it had to be at STP. We no longer have to be STP because we know that we have the ideal gas law that allows us to go between moles and volumes in any condition. So, voila, this is the new chart. We're going to be able to, if we have the volume, the temperature, and the pressure of a gas, even if it's not at STP, we can use the ideal gas law in this iteration to get to moles. And vice versa, if we have the moles of some other substance and we need to know either the pressure, the volume, or the temperature of that gas, we can use PV equals nRT in order to solve for whichever variable we're looking for, because we would obviously need the moles plus the other two. Let's look at a few examples, and the rest of this video is just going through a series of examples, a couple of them by your book, a couple of them by me, to show how we can utilize the ideal gas law and stoichiometry. So first question, it says hydrogen peroxide, that's that stuff that you put on cuts and it fizzes on you, is a common bleaching agent. It decomposes quickly in water and oxygen at high temperatures. So question is, how many liters of oxygen gas are produced at 78 degrees Celsius when 0.934 atmospheres if you start with 1.27 liters of hydrogen peroxide? Now, hydrogen peroxide is a liquid. So one of the things that's given here is the density of that liquid. It tells you how many grams there are of that hydrogen peroxide per milliliter. Now, this is a little misleading, but we're going to go with this anyway. So this hydrogen peroxide is 1.27 liters of it, and we're going to assume this is pure hydrogen peroxide. That's where the misleading part comes into play, at a density of 1.2 grams per mil. So we're going to go back to and I'm going to go back to the chart. We're actually going to start here at mass, because what we have is a volume, but we're going to use density in order to get it to mass. And then the question asks us for the volume, so we're going to end up here. So we're going to go mass to mole to volume, but we're going to use PV equals nRT in order to get to our volume. So you're given the temperature, we're going to have to change that to Kelvin. We're given a pressure, we're going to use that, we can use atmospheres. We're given a volume, it's a liquid volume, and a density, which will give us our mass. And it's asking for the volume. So our plan, like I just said, is going from mass to moles. We're going to actually go from volume to mass, then mass to moles using the molar mass, moles of H2 hydrogen peroxide to moles of oxygen using the stoichiometric coefficients, and then using the ideal gas law, we're going to get the volume of the gas. So change the mass, density times volume is going to be your mass. So our density is 1.02 times the 0.27 times 10 to the third. So we get 1.3 times 10 to the third grams, or 1,300 grams. That's a lot of hydrogen peroxide. Want to know the moles of oxygen? Well, I'm going to take that 1,300 grams of hydrogen peroxide, divide it by the molar mass of hydrogen peroxide, get my ratio from a balanced equation of 2 to 1, and I find that I could create 19 moles of oxygen gas. Again, that's a lot of oxygen. So how do I get the volume of oxygen? Well, if I use PV equals nRT, dividing both sides by P to get nRT over P, then I've got 19 moles times my ideal gas law constant R that uses atmospheres, my temperature, which is my Kelvin temperature, the Celsius temperature is going to be converted to Kelvins, divided by my pressure, and I find that I can make 588 liters of oxygen gas. That's a lot of oxygen, but then again, we said this was a very large amount of hydrogen peroxide. Okay, let's try another problem. This one also is one that I've pulled from someplace else that's very similar to the lab that we were going to do, where we're going to take a piece of zinc, we were going to use magnesium, add it to sulfuric acid. It was going to create hydrogen gas, and you're going to collect it in what's called an eudiometer. If you look at the video that is for the molar volume of a gas lab, you'll see they use what's called a eudiometer. So it's like a a graduated cylinder, a very thin, long test tube with graduations, pretty expensive piece of glassware that collects the gas. And it says if you collect 48.5 milliliters of dry gas, there's a calculation involved there to get rid of the moisture because it is going to be collected through water, and is collected at 22 degrees Celsius and 98.4 kPa. What is the mass of the piece of zinc? So in this situation, what's given to us is information about the ideal gas law. So we're going to use the ideal gas law first to get the moles from the volume, the temperature, and the pressure. And then we're going to get the moles, go to the moles of the zinc, and then use the molar mass to get the mass of the piece of zinc. Let's see how that's done. So here's our pressure, temperature, and volume. And we need to do some conversions. So we have to use volume in liters. We have to use temperature in kelvins. Those are have-tos for the ideal gas law. Then we're going to use the ideal gas law. And this time, since we have the PV and the T, we're going to solve for N to go from pressure, volume, and temperature of a gas at non-standard conditions. And we're going to convert them into moles. So I've got my pressure, my volume, my R, my temperature, and I find that I have 0.00194 moles. That's not really a lot of volume, but you're only collecting 50 mils of gas. Then we're going to use stoichiometry to say, well, it's a 1-to-1 ratio between zinc to hydrogen, and we know that zinc's molar mass is 65.39, so we would only need or only have reacted with 0.127 grams of zinc. Okay, let's do one more. This one's kind of interesting. It's kind of cool. It relates a little bit to biology. I don't know whether you guys understand the molecule hemoglobin, which is found in blood. One of the interesting things about this hemoglobin molecule, one is a very, very large protein molecule, but it actually will grab oxygen to pull it into the blood. It'll hold on to oxygen, but each hemoglobin molecule will hold on to 4 molecules of oxygen. So for every 1 hemoglobin molecule, there are 4 molecules of oxygen. So what they're asking here is, it's going to be kind of interesting, is ultimately we're going to try to find the molar mass of hemoglobin. I said it's a very large molecule, and you'll see when we're done here, it's going to get a very, very large molar mass. But we're going to take 1 gram of hemoglobin, and we're going to allow it to capture oxygen. So it will combine with a measly 1.53 milliliters of oxygen at a typical body temperature. The 37 degrees was used for that, and at a typical pressure, a little less than at 1 atmosphere at 743 torr. I'm asking what's the molar mass of hemoglobin. So what we're going to do is we're going to use the volume, the temperature, and the pressure to get the number of moles of oxygen, then tell us the number of moles of hemoglobin. And since we know the number of grams of hemoglobin, we're going to use the grams per mole to figure out the molar mass of hemoglobin. Let's see that. So we have our mass, we have our volume, we have our temperature, we have our pressure. We're going to convert our volume over to liters, temperature over to Kelvin, and then pressure, we have a choice, but in this situation, we're going to convert it over to kPa. I told you when we introduced the ideal gas law, I kind of like going to the kPa if that's an option. So we convert to kPa. We then will use the ideal gas law, solving for number of moles. And again, this is moles of oxygen. Moles of oxygen is the pressure of oxygen times the volume of oxygen divided by the temperature of oxygen, and then the appropriate gas law constant. So the pressure was 99.0 kPa. The volume was 0.00153. Since we're using kPa, the appropriate gas law constant is 8.304. And then finally, the appropriate temperature was 310.2 for a number of moles of 5.87 times 10 to the -5 moles. That's a very, 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 very small number of moles. However, this question asks us to solve for the molar mass. Well, we know that molar mass is the number of grams per mole. So first thing we have to do is figure out that the information we just got was all about oxygen. It's not asking about the molar mass of oxygen. We know the molar mass of oxygen. It's asking about the molar mass of hemoglobin. So we know that 4 molecules of oxygen will react with 1 molecule of hemoglobin, which means 4 moles of oxygen will react with 1 mole of hemoglobin. So we have a number of hemoglobin molecules, again, even smaller at 1.47 times 10 to the negative 5th moles. So a very small number of moles. We know molar mass is grams per mole. We take our grams, 1.0 grams divided by the number of moles, and we get a molar mass of 68,000 grams per mole. That's pretty close to being accurate. It is definitely over 60,000 grams per mole as being the molar mass of hemoglobin. I think the documented value is 64,000. Okay, final example. Last example we have, they talk about natural gas. Natural gas contains hydrogen sulfide as a pollutant. So we want to get rid of the hydrogen sulfide. So what they're going to do is they're going to take hydrogen sulfide and have it removed from the raw natural gas by the reaction below, where we have this ethanolamine, that's this compound right here, and it's going to react with the hydrogen sulfide to make this compound and have it removed out. The question is, how many grams of ethanolamine, that's this compound, is required to remove hydrogen sulfide from a large 1,000 cubic feet of natural gas at STP if the partial pressure, meaning the pressure of the hydrogen sulfide gas, is a very, very tiny, very paltry 205 pascals, not kilopascals, but pascals. So let's see how this works. So we have our reaction of ethanolamine with the hydrogen sulfide. Everything's 1-to-1. Wants to know how many grams of ethanolamine is needed to react with a certain volume, temperature, and pressure. There's no temperature there. Well, really it is. They say this at STP, which means the entire entire mixture has a pressure of 1 and 1.3 kilopascals, but the pressure of the hydrogen sulfide is only 205 pascals. The temperature of the gas is 0 degrees Celsius or 273.15 K. So we know our pressure is 205, our volume, the size of the container, is 1,000 cubic feet, and our temperature at STP, let's just jump to the chase, is the 273.15 Kelvin. We can't use pressure in pascals. We need to change that to kilopascals. We can't use volume in feet cubed. We need to convert that to liters. So remember when we did dimensional analysis, whereas you're going from feet cubed to inches cubed, if there's 12 inches in a foot, you have to cube everything. Same thing here. If there's 2.54 centimeters in an inch, then you have to cube everything. And that 1,000 cubic centimeters is a liter, or 1,000 milliliters is a liter. We find that the container's volume is 28,000 liters, a very, very large container we're trying to get the gas out of. So we're going to use the ideal gas law to figure out the number of moles of hydrogen sulfide we have. So we find that we have, take the 0.205 kilopascals, the 28,000 liters, the appropriate R value, and the temperature, and we find that we have 2.55 moles of hydrogen sulfide. We know there's a 1-to-1 molar relationship between ethanolamine and hydrogen sulfide, and then we use our molar mass to figure out how many grams of ethanolamine there are. So we would need, for that big room of gas, we would need 156 grams of ethanolamine. Okay, so what's next? Next time that you listen to my wonderful voice, I'll be talking a lot more about what's called kinetic molecular theory, and we're going to talk a lot more about gas movements and gas motion, how fast the gas molecules move and how do we figure that out. And then that should be the end of the chapter, which means I want to throw onto OWL an assessment to allow you to test yourself to see whether or not you really truly understand all that we did. I'm going to post that on Thursday at this point, and we'll give you a little bit of time to take care of that. And again, like the last assessment, the aqueous stoichiometry assessment, I'm going to give you multiple attempts to try to get that right to optimize your grade and practice as much as you need to in order to be successful there. I look forward to seeing you guys sometime. Hopefully you guys, again, are safe and healthy, and that everybody is abiding by Governor Hogan's edict of social distancing now, including in a stay-at-home order. I know it's going to be tough. Hopefully a little bit of time spending with your friends and classmates on Wednesday, Thursday, and Friday will help. So again, starting tomorrow, Wednesday, I'm going to have from 2 to 2:45 a team meeting set up. I'm going to send something to your email in a moment that will invite you to a team meeting. Go ahead and hit that link. Come on and join. Let's work out the kinks. If you have any questions about the owls or anything else and you want to share, please do so. I'm going to throw it out there. Gabe, if you have a joke of the day, we could really use one. So anyway, take care. Always remember, never forget, sig figs do matter. See you later.